Welcome to the new video in Discrete Math series. In this video, I will talk about pigeonhole principle and generalized pigeonhole principle. In the latter part of this video, I will also talk about principle of inclusion and exclusion and how to count the number of onto functions that we can define from one set to the other set. In case if you are new to the channel, please subscribe it so that you get good quality video content. So let's start. First of all, what is the statement of pigeonhole principle? It says that if k is a positive integer, right, and suppose k plus 1 or more objects are placed into k boxes, right, then there is at least one box containing two or more of the objects. The name pigeonhole principle is used because some authors or some people also use the statement like k plus 1 or more pigeons are suppose occupying k holes, then there will be at least one hole which will be occupied by two or more of the pigeons. Right, the statement is very simple. To understand this, I am going to take some examples as well. The pigeonhole principle is also known as Dirichlet's drawer principle. Dirichlet drawer principle. So let us look at some of the examples. Suppose we select a group of 367 people. Then using the pigeonhole principle, we can guarantee that at least two of them will have the same birthday, right? Because at most how many birthdays are possible? At most 366 possible birthdays are there. Here I am including 29th February also. So in a year there are 366 days at most if I take the leap year. So if there are 367 people, so I can consider these 367 people as pigeons, right? And these 36 birthdays, the possible birthdays that are available as the holes, right? So these 367 people have to occupy this 366 hole. It means that there will be at least one hole which will be occupied by more than one pigeon, means there will be at least one date on which more than at least two people will be born on the same date, right? See, there is a very important point that I want you to understand here, that when I am saying that at least two people have the same birthday, I am not excluding the possibility that many number of people may have the same birthday, but what I am saying is that it guarantees that if there are 367 people, then at least two will have the same birthday, right? So that is the guarantee. To understand this, you can also consider a very simple example. Suppose five of you as friend booked Goa trip, and suppose earlier four of you planned that you will be going to Goa and each of you have booked a separate room, means you have booked 4 rooms. But later on one of your friend also joined, so now you are 5 friends, but since you have already booked 4 rooms, so the next guy, and there is no more room available in that hotel where you have booked the 4 rooms, so you have adjusted with among yourself. So in that case what will happen, that there are 4 hotel rooms, which is actually equal to number of holes if I see the analogy here, and there are 5 pigeons, and you 5 of you are considering yourself as pigeons, so there will be at least one hotel room which will be occupied by more than one of your friend, right? It is also possible that since you are very good friend and you want to party the whole night, so you are staying in just one room and all other rooms are lying vacant. Yes or no? It is also possible. You agree? Okay. So let us look at the other example. Suppose you take a dictionary and you select any 27 random English words. Then using pigeonhole principle, you can guarantee that at least two of those words will begin with the same letter. Yes or no? Because how many letters are available? There are 26 alphabets, and there are 27 English words. So these English words are acting as pigeons here, and the 26 alphabets are acting as the holes. So each of the hole will be, at least one of the hole will be occupied by more than one pigeon. So it means what? That at least two of the English words will begin with the same number or same letter, sorry. Similarly, if you look at the third example, that how many a student must be in a class to guarantee that at least two students receive the same score on the final exam if the exam is graded on the scale of 0 to 100, right? So the exam is being graded from 0 to 100. So how many possible scores are there? 0, 1, 2 up to 100. So total number of possible scores that can be awarded to the students are 101. So to guarantee that at least two students receive the same score, we need to have 102 students in the class, right? Because according to the pigeonhole principle, what will act as whole here? This 101 scores will act as wholes, and now 102 student must be there, so that at least one of the whole, or at least one of the score which is varying from 0 to 100 is being assigned to at least two of the student, right? Means same score is being assigned to at least two of the students. So means what is happening here? We are taking 102 students. If I take more students, then also at least two of them will be receiving the same grade, but minimum 102 student must be there. The next thing that we are going to talk about is known as generalized pigeonhole principle, and the statement is that if n objects are placed into k boxes. Now in earlier case I was taking k plus 1 objects and k boxes. Now I am making it more general. That is why we are calling it generalized pigeonhole principle. So if n objects are placed into k boxes, then there is at least one box containing n by k, and here this symbol I am using as least integer function, and it is also known as the ceiling function. I hope in your earlier classes you must have studied about ceiling function and floor function. So there are at least n by k objects under the ceiling function which are placed in at least one of the box will contain at least n by k objects. To understand this, let us take this example. Suppose we are taking any random 100 people, right? And out of those 100 people, I can guarantee that 100 by 12, and this will be least integer function. It means 100 by 12 least integer function value is equal to 9. So 9 of them will be born in the same month. I hope you understand what is least integer function. By least integer function I mean that suppose I want to find the least integer value of 7.6. So it means what? That I am going to look at all those integers which are greater than 7, means 8, 9, 10 and so on. And out of them, which one is the least? 8 is the least. So that is the least integer value. If I take the least integer value of an integer like 7, then it will be equal to 7, right? So here 100 by 12 will be something like 8 point, because we know that 12 into 8 is 96. So I will be getting 8 point something. I don't exactly know what it will be, but it will be 8 point something. And if I take the least integer value of 8 point something, that will be the next integer, which is equal to 9, because the least integer which is greater than 8 point something will be 9. Look at this problem. What is the minimum number of students required in a discrete maths class to be sure that at least 6 will receive the same grade, right? And here there are 5 possible grades. What are those 5 possible grades? A, B, C, D, and F. So basically, how many boxes are there, or how many holes are there? There are 5 holes, right? So to guarantee that at least 5 of them receive the same grade, suppose I say that we require minimum number of a student n, and n by 5 should be equal to 6. This is what we require, because you look at the statement, the greatest integer function value n by k, and then we take the ceiling function. You saw the notation that we are using is like we are drawing a ceiling, and similar kind of thing you have studied about, like floor function, which you also called greatest integer function. So the notation that we used for floor function, in case if we are using this notation for ceiling function, we use this notation for floor function. So suppose I say that there are n what we need students, and if there are n students, then n by 5 with the ceiling function should be equal to 6. So what will be the value of n? The value of n that we have to take, suppose I take n is equal to 5 into 5. So if I take 5 into 5, what will happen? I will get equal to 5, because 5 into 5 by 5, if I take its ceiling function value, then 5 and 5 will cancel and I will get 5. So certainly I have to take at least one more. So 5 into 5 plus 1, that is equal to 26. So if we have 26 students, right, and there are 5 possible grade, then at least 6 of the students will receive the same grade, right? This is how the generalized pigeonhole principle works. I hope you have understood the things. Let us take this problem here just to understand it, that in a drawer that contains 12 red and 12 blue socks, all unmatched, it has been put in the drawer randomly, and a person takes socks out at random in the dark, means suppose the light is off and there is it is not visible that whether the socks are blue or red. So how many socks must be taken out to be sure that he has at least 2 blue socks? So here also you can use kind of pigeonhole principle, and to understand this, let us look at this argument like this. What is the worst case scenario? What is the worst case scenario here? That the person is taking out socks at random, and the first 12 socks that he has drawn are all red. It is a possibility because we want to guarantee it, yes or no? Because we want to guarantee that we want to be sure that at least 2 of the socks are blue. Now first 12 socks may be all red, that is also a possibility. Now the next thing, that next socks that he will draw will certainly be a blue socks. But he wants a pair of blue socks, so he has to draw the 14th socks. So in that case it will be guaranteed that he will have a pair of blue socks. Are you getting my point or not? See, the important thing that you need to understand here, that you want to be sure, and sometimes you become very unlucky that every time you are drawing the socks and it is coming to be red, right? So if you have drawn first 12 socks and suppose all of them are red, but the 13th, the moment you draw the 13th socks, it must be a blue socks. So to ensure that at least 2 of the socks are blue socks, you must have to draw minimum or at least 14 socks. So the correct answer will be 14. Okay. So let us talk now about principle of inclusion and exclusion. So first of all, I take this 2 set example, and I think you must be aware that if I have to count the number of elements in A union B, it is equal to number of elements in A plus number of elements in B minus number of elements in A intersection B. Here this symbol I am using to represent the number of element in that particular set. So the first question based on this idea that suppose we have to find how many positive integers not exceeding 1000 are divisible by 7 or 11, right? So first of all, I count the suppose I say that A is the set which contains all the integers which are divisible by 7. So this contains all integers divisible by 7, and B is the set which contains all integers divisible by 11. Now how many elements are there which are divisible by 7? So up to 1000, the total number of integers which are divisible by 7. So I take the greatest integer function value, right? In the previous example, when I was talking about generalized pigeonhole principle, I was taking the ceiling function. Here I am taking the floor function, and the greatest integer function value or the floor function value is calculated by taking the greatest integer which are less than. For example, to understand, suppose I ask you what is the floor function value of 7.9. So that will be equal to 7, because all the integer which are less than 7, out of that which one is greatest? 7 is the greatest. If I ask you what is the float function value of 2.3, so the answer will be 2. If I ask you what is the float function value of integer 4, so in that case it will be 4. So just to count the number of integers which are divisible by 7, I will divide 1000 by 7 and I will get 142 point something. So its integral part will be 142. Similarly, the total integers which are divisible by 11, so I will take 1000 divided by 11 and then I will take its greatest integer value, so that will be equal to 90. It will be 90 point something, so I will take the integral value, that will be equal to 90. So to count the total integers which are divisible by both either by 7 or 11, so I am going to count. So there will be certain integers which will be divisible by both 7 and 11, and I think you are smart enough to understand that those integers which are divisible by both 7 and 11 will also be divisible by 77. Yes or no? Basic idea. So if you divide 1000 by 77, it will be equal to 12. So basically the number of elements which are either divisible by 7 or 11 is A union B. If I calculate number of integers divisible by 7 plus number of integers divisible by 11 minus number of integers which are divisible by both 7 and 11. So it will be like 142 plus 90 minus 12. So that will be equal to how much? That will give you the answer. So let us calculate that. So that value will be 130 plus 90 is equal to 220. So you see that in case of two sets, we have understood that if we have to count the number of elements in their union A and B, then we take the number of elements in A and plus the number of elements in the set B. And I think you note here that when I am taking the number of elements in the set A and set B, we are counting this part which is common twice, once from A and another when we are counting the elements from B. So since we are counting it twice, we are removing it once, right? Now let us take the example when there are three sets. So in case of A union B union C, this formula is like the number of elements in A plus number of elements in B plus number of elements in C, and then we subtract the intersection of two of them. So A intersection B, B intersection C, and C intersection A, and then we add them, the intersection of all of them. And in case if you want to draw the Venn diagram, that will help you to understand. But I am solving this problem now. So a total of 1232 students have taken a course in Spanish and 879 have taken a course in French and 114 have taken a course in Russian. So let me write the information that is provided together. So we will read the question and we will also extract the information that is available. And I am using the Spanish set, the set of a student who have studied Spanish, as the set S. So total number of elements in set S is 1232. Those who have studied French, I am calling them the F, and that is equal to 879. And those who have studied Russian, so it is equal to 114. Further, 103 have taken courses in both Spanish and French. Means as both Spanish and French means Spanish intersection French, that is equal to 103. And 23 have taken courses in both Spanish and Russian. So Spanish and Russian is equal to 23. And 14 have taken courses in both French and Russian. So French intersection Russian is equal to 14. If 2092 students have taken at least one of the Spanish, French and Russian, how many students have taken a course in all the three languages? So basically the information, the last information that they are providing is S union F union R, means this information that if 2092 students have taken at least one of Spanish, French and Russian, that is equal to 2092. If you see the Venn diagram to understand this picture, suppose this is the Spanish, this is the French and this is the Russian, right? So if I take any element from this, means that is the union part, right? And then there are intersection between Russian and French and intersection between French and Russian and so on. So what they are asking that how many students have taken a course in all three languages, means Spanish also, Russian also and French also, means they are asking that what is the intersection of all of it. So for three sets we already have the formula, so we are going to calculate S union F union R is equal to the number of elements in S plus number of elements in F plus number of elements in R minus number of element in S intersection F minus S intersection R minus F intersection R and plus S intersection F intersection R. Now this information is provided to us, though this information is 2092 and then it is equal to 1232 plus 879 plus 114 minus 103 minus 23 minus 14 and plus that I have to calculate number of elements in S intersection R intersection F. So if you simplify this expression, I am writing the answer for you. S intersection R intersection F will be equal to, you bring all these terms in the left hand side, so this will become minus 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 and this all will become plus, so the value will be equal to 7. You can verify it, that you keep it in one side and take all other values in the other side. So the total number of students who have taken both Spanish, Russian and French is equal to 7. So I wanted you to notice 2-3 important points here. The first important point that I wanted you to notice, that if you talk about two sets, if you are counting the total number of elements in the union of two sets, it has 3 elements in the right hand side, A, B and A intersection B. If you are counting the number of elements in the union of 3 sets, it has 1, 2, 3, 4, 5, 6, 7 elements, right? Now the question is that can we write a general formula to count the number of elements in a set in the union of a set with n elements. Let me rephrase my statement. I am asking that we are looking for a formula to find the union of n number of different sets. So to count the number of elements in the union of n number of different sets, we have a formula, and that is known as the formula for principle of inclusion and exclusion. And here you can see that A1 union A2 union up to AN. So we have n sets. So first what we do, first we take one set at a time and then we add it. So I take A1 set of A1, number of elements in A1 plus A2 and up to AN. Then we take a minus sign and subtract the number of elements in which are common in two of the sets. So I take all possible two pairs which I can take from these n sets. So like I can take A1 intersection A2, A1 intersection A3, A1 intersection A4 and so on. Then we take three of them at a time, and here you see that the signs are changing alternatively. So first I added all of them when I am taking one of them at a time, and when I am subtracting two of them at a time, so I am subtracting them, and then we are adding the combination or intersection of three of them at a time, and so on. So in the end we take intersection of all of them. I think if you are getting confused with this, I am taking one example which will help you to understand this better, right? So suppose I ask you that give me a formula for the number of elements in the union of four sets. So suppose I say find the number of elements in A1 union A2 union A3 union A4. So first thing is that it will have 15 terms in the right hand side, because when we had two sets we had three terms, that was 2 square minus 1. When we took three sets, then we had 7 terms, that is 2 to the power 3 minus 1. When I'm taking 4 sets, then we will have 2 to the power 4 minus 1, that is 15 terms. So the principle of inclusion and exclusion tells me that first take A1 one set at a time and then take the sum of this. So A1 number of elements in A1 plus number of elements in A2 plus number of elements in A3 plus number of elements in A4, right? Then we are going to take two of them at a time and we are going to subtract. So I'm writing minus. And how to take two of them at a time? So I take A1 intersection A2, right? Then I take A1 intersection A3. Then I take A1 intersection A4, right? And then I take A2 intersection A3. Then I take A2 intersection A4, and then I take A3 intersection A4. And see, ladies and gentlemen, there will be 6 such pair, because if I have to select two sets out of 4 sets, that can be done in 4C2 ways, that is factorial 2 by factorial 2 into 2. So that is equal to 4 into 3 by 2. So actually 6 ways are there. Now plus minus, now I am going to take 3 of them at a time. So I will add them, and 3 of them at a time will be like A1 intersection A2 intersection A3, then plus A1 intersection A2 intersection A4 plus A2 intersection A3 intersection A4. And what more I can write? I can write A2, A3, A4 I already have written. So I can write now A1 intersection A3 intersection A4. I hope these are all different. A1, A2, A3, A1, A2, A4, A2, A3, A4 and A1, A3, A4. So these are all distinct elements and 4 of them are there. And finally I subtract A1 intersection A2 intersection A3 intersection A4. So we saw that how to find the union of 4 sets. Let me repeat it one more time. So the idea is that if I am taking the union of n number of sets and counting the number of elements in that, first we take one of them at a time. So here we have 4 of them. So a1 plus a2 plus a3 plus a4, and this is the number of elements. So don't confuse that we are adding the set, we are adding the number of elements in the set. Then we take two of them at a time, so there are 6 pairs. So a1 intersection a2, a1 intersection a3, a1 intersection a4. And one more thing that you need to understand, that when I'm writing it, I'm writing in a very systematic order, like a1 and then I'm taking its intersection with a2, a3 and a4. Then I'm taking a2 and a3 and then a2 and a4 and finally a3 and a4. So every time I'm keeping the element, like if you look at this formula, that we are keeping this I less than j when I'm taking ai intersection aj. And similarly, when I'm taking the intersection of 3 of them, I'm keeping I less than j less than k, right? So when I'm taking 3 of them at a time, so I'm taking a1, a2, a3, then a1, a2, a4, then a1 a2, a3 and a4, and then a1, a3 and a4, and finally I have taken 4 of them together. So this is how we can write the union of 4 sets, which counts the number of elements in their union. Next thing that we are going to talk about is the number of onto function, how to count the number of onto function. And this is an important idea which is based on the principle of inclusion exclusion. There is a generalized form of that also. We are not going into that detail, but because this is a very important result, and lot of interesting question can be solved based on this result. So I'm directly jumping to that and trying to explain you. I will be taking 2 problems based on this as well. First of all, I hope all of you remember that what is an onto function. In your school days, you must have studied that suppose we have a set A and we have a set B, then the number of what is an onto function? So onto function is a function that which says, that definition says that for every element in the codomain, if I call this set as domain and the set B as codomain, so for every element in the codomain, suppose we have the elements here y1, y2, y3. So every element must have a pre-image. Suppose I have x1, x2, x3. So every element, suppose I say x1 is related to y1, x2 is related to y2, and x3 is related to y3. So every element here has a pre-image, and in that case it is said to be an onto function. There may be a situation like, suppose I take this example where I am taking 3 elements like a, b, c here, and here I am taking elements like 1, 2, 3, and I am saying 1 is mapping to a is mapping to 1, and b is also mapping to 1, and c is mapping to 2. So this element 3 does not have any pre-image in the first set. It means it is not an onto function, right? This is known as into function, I-N-T-O, into function. So basically, some people also define the onto function as that the codomain and range both should be equal, right? So all those elements which are present in the other set must have a pre-image in the first set. So the question is that if we have a set with m number of elements and another set with n number of elements, and the number of elements m may be greater than or equal to n, so m is either greater than or equal to n, then how many onto functions can be defined? So the number of onto function is equal to n to the power m minus nc1 n minus 1 to the power m plus nc2 n minus 2 to the power m, and so on. How to remember this? Let us look at this. One thing that you see that I am taking n to the power m here. So and then the other terms has means the n is decreasing. So here we have n, here you have n minus 1, here you have n minus 2, and there are total n terms. One thing also you can just for understanding purpose, you can assume that here we have nc0, right? You can just assume that here we have nc0. We know that nc0 is equal to 1. So n to the power m, nc0 n to the power m, nc1 n minus 1 to the power m, nc2 n minus 2 to the power m. So the power is always m. Power is always m. N to the power m, n minus 1 to the power m, n minus 2 to the power m. Second thing is that the sign is changing alternatively. The first is positive, then negative, then positive, then negative, and so on. And the last term is nc n minus 1, 1 to the power m. So it is decreasing, n, then n minus 1, then n minus 2, and going up to 1. To understand the application of it, I think it will help you to understand better. Let us look at this problem. How many ways are there to assign 5 different jobs to 4 different employees if every employee is assigned at least one job? So let us look at this problem like this, that there is a situation where how many jobs are there. Suppose I say that there are 5 jobs, J1, J2, J3, J4 and J5. And how many employees are there? So number of employees are E1, E2, E3 and E4, 4 employees. So the number of elements in the first set is 5 and the number of element in the second set is 4, means this is equal to M and this is equal to N. So we are defining the mapping from this set to the other set, and clearly you can see the first requirement is that M should be greater than or equal to M is satisfied because 5 is greater than or equal to 4. Now this problem can be seen as a problem related to counting the onto function, because we want what? We want that every employee must be assigned a job, means none of them should be left out. E1 must have a job assigned to him. Employee 2 must also have a job assigned to him. So none of the employees should be left out, and that is what the requirement of onto function, that none of the elements should have every element should have a pre-image. None of the elements should be left out. So if I have to count it, the total number of ways of assigning jobs to these employees in such a way that every employee get at least one job, can also be seen as a problem related to counting the number of onto function from a set with 5 elements to a set with 4 elements. Got my point? I repeat this. How many employees are there? 4. How many jobs are there? 5. Everyone must be assigned at least one job, means there should be no one left out here, means that mapping that we are defining should be an onto mapping. So how many possibilities are there? So let us answer this question and count the number of ways of assigning the jobs in such a way that at least, so what is the total number of ways? I am writing total number of ways, and that is equal to, ladies and gentlemen, so here our M is 4 and N is M is 5 and N is 4. So first is N to the power M. So I will write 4 to the power 5 minus NC1, means 4C1, and what will be the next term? Next term will be 4 minus 1 to the power 5, minus sign, with a minus sign, plus 4C2, 4 minus 2 to the power 5, right? Then minus 4C3 and 4 minus 3 to the power 5, right? Now you noted that how many terms I have written? 1 term, 2 term, 3 term and 4 term. So here we require how many terms? N terms. Here also we require how many terms? 4 terms, because n value is equal to 4. I hope I want you to understand this formula clearly, that we are starting from 4 to the power 5 and going up to 1 to the power 5, because 4 minus 3 to the power 5 is 1 to the power 5. So if I simplify this, 4 to the power 5 is 1024 minus 4C1. So if you 4C1 is equal to 4 and into 3 to the power 5. So if you calculate, this value will be 972. 4C2 and into 2 to the power 5. So if you calculate, this value will be 192, and minus 4C3 is equal to 4 and 1 to the power 5 is 1. So it will be 4. So what will be the answer? The answer will be 240. So there are 240 ways to assign 5 different jobs to 4 different employees, so that at least every employees get at least one job. Now let us look at this problem. How many ways are there to distribute 6 different toys to 3 different children, such that each child get at least one toy? So here also we have a situation where we have to count the number of onto function. So what is the situation here? That we have six different toys. So means we have toy 1, toy 2, 2i 3, 2i 4, 2i 5, and 2i 6. And how many children are there? There are 3 children, C1, C2, and C3. You usually don't want the child to be left out. There must be some favored child, but every child is special, yes or no? So everyone must get at least one toy, otherwise they will feel left out. Now to count the number of ways in which that can be done, so basically here the idea is that we have a set M with 6 element, means there are 6 toys, and we have a set N which has 3 elements, and we want every element here, means in every child here must get at least one toy. So I am going to count the number of onto functions. So what is the total number of onto function? Total number of wage is equal to distribute the toys is what is the formula? So the formula is n to the power m. Yes or no? So n to the power m here is here n is equal to 3 and n is equal to 3 and m is equal to 6. So I will take 3 to the power 6. Now nc1. So I will take 3c1 and n minus 1. So that is 3 minus 1 to the power 6. So plus minus, then third term will be plus. nc2 means 3c2 and 3 minus 2 to the power 6. Yes or no? Now 3 minus 2 to the power 6 will become 1. So we already have written 3 terms. I hope you are getting this point. If n is equal to 3, so in the expansion here, when I am counting the number of onto function, there will be 3 terms. So 3 to the power 6, 3 minus 1 to the power 6, 3 minus 2 to the power 6, and that will give me 1 to the power m type. So the last term is actually 1 to the power m, and 3 minus 2 is nothing but 1 to the power 6. So 1 to the power 6 is there. So 3 to the power 6, if you calculate, will be equal to 729 minus 3c1 is equal to 3 and 2 to the power 6. So I write 2 to the power 6, and 3c2 is also equal to 3, and into 1 to the power 6 basically is equal to 1. So what we get? We get 729 minus 192 and plus 3. So if you simplify, you get 540. So this is the answer. This is the total number of ways in which you can distribute 6 different toys. So at least every child must at least get one toy. Okay. So that is all, ladies and gentlemen, for this video. We have discussed a lot of interesting things. This video actually, if you must have watched this video, then I guess you have learned a lot of interesting things here. So in case you liked it, please press the like button, share with your friends, and let it reach to the maximum number of people, so that they also get benefited from the efforts that I am putting. Thanks for watching and have a great day.